Welcome back to The Explainer. Today, we're taking some pretty dry thermodynamics and translating them into massive, high-stakes engineering decisions. Because if you've ever wondered how isolated industrial behemoths actually keep the lights on and the machinery pumping when they're, hundreds of miles away from the nearest utility grid, well, you are definitely in the right place.
Okay, let's set the scene. Picture yourself standing out on the deck of an FSPO, a floating production, storage, and offloading vessel, smack in the middle of the Gulf of Mexico. It's 2 a.m. The ambient temperature is a sweltering 35 degrees Celsius, and the humidity is pegged at nearly 100%. It's pitch dark, the air is heavy, and you can literally feel the steel deck vibrating right beneath your boots. We really need to understand the stakes out here, where a single piece of machinery is the only thing keeping the entire platform from going totally dark.
So that deep vibration you're feeling, that is a gas turbine generator running at a blistering 3,000 revolutions per minute. To put that into perspective, just imagine a machine roughly the size of a school bus spinning 50 times every single second. Crazy, right? It's continuously burning raw wellhead gas to produce absolutely every single watt of electricity needed on board. It is the beating heart of the platform, and understanding exactly how it survives and operates in this brutal environment isn't optional. It's literally a matter of survival.
All right, here's our roadmap for today. First, the thermodynamics at play. Second, real-world power derating. Third, choosing your gas turbine. And finally, governing turbine speed.
Section 1. The thermodynamics at play. The Joule cycle. So the gas turbine operates on the simple Joule cycle, which you might also know as the Brayton cycle. It's basically an intense, continuous journey of airflow. Step 1, the compressor violently pulls in and squeezes ambient air. And we're not talking about a gentle breeze here. These machines gulp down hundreds of pounds of air every single second. Step 2, that super dense, highly pressurized air mixes with fuel and ignites in the combustion chamber. Then step 3, that volatile, rapidly expanding hot gas blasts its way through the power turbine, translating all that insane thermal energy into pure mechanical rotation.
But here's a really staggering engineering reality. A massive 50 to 60% of the gross turbine output goes straight back into driving its own air compressor. You'd think all that power goes to the generator, right? Nope. The machine consumes a huge chunk of its own energy just to keep itself breathing. That leaves only the remaining 40 to 50% as your net shaft output to actually spin the generator and power the rig.
Section 2. Real-world power derating, when physics meets reality.
When you buy one of these turbines, the manufacturers rate their machines under perfect laboratory-grade ISO conditions. We're talking sea-level elevation, a crisp 15 degrees Celsius ambient temperature, and a perfectly clean engine fresh off the pristine factory floor. But here's the catch. You are not operating in a sterile lab. Whether you're stationed out in the sweltering Gulf of Mexico, the dusty Middle East, or the humid coast of West Africa, you are almost never, ever going to operate in those ideal parameters.
And this brings us to a massive dilemma for engineers. As the ambient temperature rises out there on a hot offshore rig, the air physically expands and becomes less dense. Since the compressor moves a fixed physical volume of air, less dense air means you're getting less actual mass flow through the engine. The result? As the temperature goes up, your turbine loses a very significant amount of power capability. So what does this actually mean for you? Well, the rule of thumb is that for every single degree Celsius rise above that perfect 15 degrees, you have to derate your power by about 0.5 to 0.8%. Do the math on a 40-degree day, which is 25 degrees above the baseline, and boom, you instantly lose over 16% of your platform's total power output, just because it's a hot day. That is a massive hit to your operational capability.
And it gets worse, because the physical environment just keeps taking its toll. These percentage losses stack directly on top of your temperature derating. Add in a 5% loss for dirty compressor blades, aging and salty, corrosive ocean air. Subtract another 1.5 to 2% lost as heat in the mechanical gearbox. Then shave off another 2 to 4% for generator inefficiency. It's basically a constant uphill battle. That pristine ISO rating you paid for on paper shrinks drastically once it actually faces the real world.
Section 3. Choosing your gas turbine. The heavyweight bout.
Now we get to a fundamental choice. On one side, we have the aeroderivative turbine. Think of this as the sports car of the turbine world, like the legendary GE LM2500 or the Rolls-Royce RB211. It's essentially a modified aircraft engine. It's super light, compact, and hits a really high efficiency of 34 to 40%. But just like a high-performance sports car, it comes with highly complex maintenance.
On the flip side, we have the heavy industrial turbine, like the massive G Frame 5 or the Solar Taurus. This is your tractor. It's heavy, immensely robust, and boasts much longer intervals between overhauls. The trade-off is a lower efficiency, around 28 to 34%, and it needs a ton of heavy floor space. So, given the severe physical constraints of offshore rigs, the application of these machines becomes crystal clear. Out on the ocean, literally every single kilogram matters. Because of that extreme weight limitation, those lightweight, modular aeroderivatives are overwhelmingly chosen for weight-critical platforms, where you can easily just swap out the entire engine for maintenance. Conversely, the heavy industrials totally dominate large fixed onshore plants like refineries, where space and weight really aren't an issue, but running continuously for years on end is absolutely paramount.
Beyond just picking the class of turbine, you also have to choose its mechanical configuration. With a single shaft drive, the compressor, turbine, and generator all share one long, rigid shaft. Because of all that spinning inertia, it responds incredibly fast to sudden power demands. Now, a two-shaft drive, which is typical of aeroderivatives, has a separate power turbine. While that gives you better overall thermodynamic performance, it suffers from a slight delay in response time. And trust me, response time is critical when a sudden, massive electrical load hits your system and threatens to drag down your entire power grid. You need that machine to react instantly.
Section 4. Governing turbine speed.
Offshore power systems are entirely self-contained. There's no massive public utility grid to lean on for stability. That means the turbine's control system, the governor, is literally the only thing keeping the frequency stable. Run it open loop, and the system is completely unstable. When a massive induction motor, say a giant pipeline pump, starts up directly on the line, it pulls an immense amount of current, aggressively trying to drag the whole system's speed down. The governor has to instantly detect this droop in frequency and precisely blast more fuel into the combustion chamber to catch that load before the whole platform blacks out.
Which brings us to the ultimate engineering test, and a final thought to leave you with. Imagine that 2 a.m. scenario again, but this time, normal power has completely failed. The ocean is pitch black. The platform is entirely dead. How do you execute a black start on a massive, heavy turbine using nothing but a stored battery bank or a fully charged compressed air receiver? Seriously, how do you wake the beast back up from absolutely nothing? Think about that engineering marvel, and I'll catch you in the next explainer.